This is the fourth lecture on Schrodinger equation in 1D. Today we shall discuss or solve the problem of one-dimensional rectangular symmetric finite potential well. Earlier we have solved the similar problem with infinite potential. Here we consider the finite potential case. Since the potential discontinuity is finite, the particle is subjected to non-impulsive force at the walls. So we can, in this case, we can apply the continuity of the first derivative of the wave function. Remember that in the case of infinite potential well, there were the existence of impulsive force at the walls of the well, so that we did not apply the continuity of the first derivative of the wave function. We divide the entire there is a well which extends from minus a to plus a, that is its width is 2a. The potential is constant here within the well, and which we have assumed to be v0, and the potential on the left and the right of the well is the potential within the well is 0, and on the left and right of the well it is v0. Since we are considering the bound state problem, the energy of the particle is E less than V0. We initialize the system that a particle of mass, a quantum particle of mass m, is originally residing within the well with energy E less than V0. So initialization of the problem. Particle of mass m is within the well with E less than V0. Our interest is to find out what are the possible energy values accessible to the particle. So we divide the entire region in three parts. Region 1 to the left of minus a, region 3 to the right of plus a, and region 2 is between plus minus a. And we write the Schrodinger equation. In region 1, the wave function is phi 1, so it is phi 1 double prime minus rho square phi 1 is equal to 0, with rho square is equal to twice m v0 minus e upon h line square, and since v0 is greater than e, it is a positive quantity. The physically acceptable solution is phi 1 at x is equal to a e to the power plus rho x, because it is this wave function prevails in the negative x region, and as x tends to minus infinity, this wave function goes to 0. So the range of applicability of this region is x less than minus a. In the region 2, the wave function is phi 2 double prime plus k square phi 2 is equal to 0, where k square is equal to twice m e by h line square, and it is again a positive quantity, and the solution is phi 2 of x is equal to b sin kx plus c cos kx. From our experience that we gathered in the case of infinite potential well, that the particle, since the particle moves back and forth within the well, there was a possibility of getting stationary waves. Keeping this in mind, we have assumed this sinusoidal solution in the form of stationary waves. Here the particle will move back and forth within the well, although since the well has finite width, there is a probability of tunneling at the well. Still we will have the reflected wave will have slightly less magnitude than the incident wave, still a stationary waves type pattern will be formed, and the range of accepts this should be that. And for region 3 we have phi 3 double prime minus rho square phi 3 is equal to 0. Again, rho is same, and physically acceptable solution is d e to the power minus rho x with range of validity is x is greater than a. So these are the three wave functions. We first write the wave functions and remember these two definitions. So this is a lengthy calculation, so larger space will be required. So I am just writing the conclusion, that is this step, this step, this step, this, and erasing all others. So phi 1 is equal to a e to the power rho x. Phi 2 is equal to b sin kx plus c cos kx. Phi 3 is equal to d e to the power minus rho x. Rho square is equal to twice m v0 minus e by h line square, and k square is equal to twice m e upon h line square. Now the boundary condition. Phi 1 at minus a is equal to phi 2 at minus a. This leads you to phi 1 prime at minus a is equal to phi 2 prime at minus a. This is rho a e to the power minus rho a. When we differentiate this, this will be b cos kx. This will be minus c sin kx times k. If we put now x is equal to minus a, this becomes plus. So this is equal to this is equation 1, this is equation 2. Then we apply the boundary condition on the right one. This is phi 2 at plus a is equal to phi 3 at plus a. For the sake of simplicity, we write three part first. So this is d e to the power minus rho a is equal to b sin ka plus c cos ka. This is equation 3. And phi 2 prime at a is equal to phi 3 prime at a. This gives you minus rho b e to the power minus rho a, and simply if we differentiate this, we will have k times b cos ka minus c sin ka. This is equation 4. Now let me manipulate. If we add and subtract these two, firstly we add 1 and 3, what we get? If we add 1 and 3, we see that this term goes, so we will have 2c, we will have 2c cos ka, 2c cos ka is equal to 1 and 3 is being added, so a plus d e to the power minus rho a. We then subtract 1 from 3, so this is 3 minus 1. This term will be cancelled and this will appear with 2, weightage 2. So this is 2b this is d minus a rho a. We call this as equation 5, this as equation 6. Then we add 2 and 4. If we add 2 and 4, we see that this term gets cancelled, so we will have twice k b cos ka adding this 2, so this term gets cancelled, twice b cos k, and on the right hand side we will have a minus d rho a. Similarly, if we subtract 4 from 2, if we subtract 4 from 2, so 2 minus 4, so this term gets cancelled and c sin ka will be there. K will be there, and 2 minus 4, this is rho times a plus d. These are equations 7 and 8. We see that in 5 and 8, a plus d appears. So we divide 5 and d. 5 and 8. So we get what we get. Eight divided by 5, equation 8 divided by 5, this gives you cot ka, sorry, tan ka is equal to rho by k. Here, when we divide, we have assumed that with the assumptions underlying are that c not equal to 0 and a plus d is not equal to 0. This is our assumption. Now we see that these two terms are again similar. We can find out cot k from here. 7 divided by 6 gives you cot Ka k by rho. Here the assumptions that we have made is that b not equal to 0 together with a minus d not equal to 0. This is the assumption because the quantity we have divided this two. What does these two lead to? Just a minute, let me check the calculation. Okay. So if we multiply these two equations, we get plus 1 is equal to minus 1 opposite. So what is the wrong in it? The wrong is in this assumption. These assumptions are not correct. That is, we may have b is equal to 0 and a is equal to d. So b is equal to 0. So one alternative is the or since 1 b is equal to 0 and a is equal to d. Let's see what happens. B is equal to 0, there is no sign term, and a and d are equal. This is even state, and alternative 2 is c equal to 0 and a is equal to minus b. Sorry, this is a should be equal to d and this is a is equal to minus d, because for in the first case b is equal to 0 and this is also 0, so a is equal to d, and in this case c is equal to 0 and a is equal to minus d. This is the odd case. So through this lengthy calculation, we come to the conclusion that the wave function for a symmetric well can be split up into two categories, and the categories are like this. Even state. For even state, the wave function is phi 1 is equal to a e to the power plus rho x, phi 2 is equal to b is equal to 0, say sine cos kx, and phi 3 is equal to, since a is equal to d, a is equal to minus rho x. You see that if we change this from our function here to there, nothing changes, simply x changes by minus x. And then the odd state, phi 1 is equal to a e to the power plus rho x, phi 2 is equal to b sine kx and phi 3 is equal to minus a e to the power minus rho x. If we take from plus x to minus x, this part changes for a sign. So this is the odd parity state. Has come to a very simplified version. The wave function either belongs to even parity states or odd parity state. If we go on further calculation, we need to apply boundary condition at any one of end of the wave. So we go on with even states. Boundary condition is phi 2 at A is equal to phi 3 at A. This gives you even state phi 2 is C cos Ka is equal to A e to the power minus rho A, and then phi 2 prime at A is equal to phi 3 prime at A. This is, when you differentiate it, it will be minus ck sine kx, and if we put it minus ck sine ka is equal to minus rho a into the power minus rho a. So the minus sign goes, or we will have c sine ka is equal to rho by ka e to the power minus rho a. If we divide this, we get cot ka is equal to plus k by rho. This is the equation. For even state, it is cot ka is equal to k by rho. Now coming to odd parity states. Again, phi 2 at A is equal to phi 3 at A. This gives you, for this odd case, this is B sine Ka is equal to minus A e to the power minus rho A, and phi 2 prime at A is equal to phi 3 prime at A. This gives you bk cos ka is equal to minus rho minus and minus plus odd state, there is a plus, yes, it is plus rho a e to the power minus rho a. So check this three. Phi 3 is equal to minus a minus rho e to the power minus rho x. So this is a rho e to the power minus rho x at x is equal to a. This is this. And if we calculate again cot k, or this is, or b cos ka is equal to rho by k a e to the power minus rho a. This gives you cot ka minus rho by a. sorry, rho by k. This is for odd state. So the solution has been decoupled into classes. The one is this, another one is this. You note that k, the dimension of k is inverse of length. So Ka is a dimensionless quantity. So we define U to be Ka. It is a dimensionless quantity. And so we consider rho square. Note the definition: twice m h line square v0 minus e. This part is twice m v0 by h line square. This is 2 minus k square. You see the definition of k square: twice me by h line square. If we multiply all the sides by a square, so we get a square rho square is equal to twice m a square v0 by h line square minus a square k square. Since rho is a real quantity, the maximum value of k square is given by 2m v0 by h line square. In that case, we write it as a square km square minus a square k square. That is to say, rho A is equal to if we call it um square minus u square under root, where we define um square is equal to twice m a square v0 by h line square. We write it m a h line square times p, where p is equal to twice a v0, strength of the potential, strength of the well. So these quantities can be rewritten. Let me once again, we have from dimension variable, we have switched over to dimensionless variables. So in terms of dimensionless variable, u is equal to km. We write it as cot u. This is u by, we multiply both the numerator and denominator by a. So this is as u is equal to 0, this part is 0, and as u tends to this goes to plus infinity. This part again, cot u is equal to minus square by u square square root by u. As u goes to 0, this goes to minus infinity, and as u goes to tends to this tends to 0 minus. And let me remember the definitions of u is equal to Ka, and is equal to here is this m a p by h line, with p is equal to twice a v0, the strength of the potential. Now these two transcendental equations has to be solved. So we write this quantity y1 is equal to u by square by u square with square root. So y1 goes to 0 as u goes to 0, as u tends to 0, and y1 tends to plus infinity as u tends to minus, because you cannot go out of this. If u approaches from the right hand side, then rho will be complex, and we write u odd is equal to u odd tends to minus infinity as u tends to 0, and u odd tends to 0 minus as u tends to minus. These are the informations. Now in the case of infinite potential well, we got the solution in the closed form, that is by putting the value that either cos k has to be 0 or sin k has to be 0. Here the situation is not like that. So we to get the energy eigenvalues, we are to solve this transcendental equation. This is equal to cot u is equal to y even, and this is equal to y odd. With this information, I am going to solve this equation. Remember these the quantities. Let me first plot cot u. This is 0, pi, 2 pi, 3 pi, 4 pi. These are the middle portion, pi by 2, 3 pi by 2, 5 pi by 2, and so on and so forth. Now, the Chord function. The Chord function is check yourself that these are indeed the behavior of the Chord function. Now y even, the property of y even, it is 0 at x u is equal to 0, and approaches as this is the line. So what this is y even. Y odd is approaches 0 from negative side at u is equal to and goes to minus infinity. So these are the graphs. You see that this part has been you see that the chord function is positive only in the first half. First half chord function is positive only in the first half and is negative in the second half. Y even is always positive. So the intersection of chord function with y even takes place only in the first half of the each cycle of pi. This is pi, this is 2 pi, this is 3 pi, 4 pi. So as we have shown in this case, if um is greater than 4 pi, it is a real, is a dimensionless quantity. So if is greater than 4 pi, there are 4 intersections of 1, 2, 3, 4, 5 intersection from even states, and also there will be an intersection 5 intersection from the even states, and there are 4 intersections from the odd states. The k values are u values correspondingly. First u values, that is u0, is less than pi. Pi by 2, pi by 2. So this is the first state that we get u0, and it comes from even parity state. Then it is u1. So what happens? u0 is less than pi by 2. u1 is less than pi, greater than pi by 2. Then this is u2. u2 is less than 3 pi by 2. And so on and so forth. So we see the greater the strength of the potential, the greater the strength of the potential, the greater is the number of bound states that it can hold. In the case of infinite potential, well, the strength is, this line is at infinity, and we have infinite number of bound states. If we have a very shallow well, that is V0 is very small, then comes very closer to this. But this line, this line, say, but line is there. This is the line. So there will be at least one bound state that comes from the even parity states, and the lowest energy corresponds to an even parity states. The first excited state has an odd parity, second excited state has an even parity, and so on and so forth. And this can give you a general relation that if lies between this to this, what will be the number of bound states. Say if we have un, then this will be less than 2. It will depend on even on odd number of states, but depending on the position of maximum value of we can count the number of bound states. This is so far the energy is concerned, and this is the way you are to find out the energy of a particle when subjected to an infinite potential. Well, the problem is included in your practical syllabus. Now I am going to sketch the wave function. To make the thing clear, I will fire infinite well and finite well to side by side. For infinite well ranging from -a to +a, the wave function in the first state is this. And for finite well, from extending from minus a to plus a, the wave function is not zero. It has some, it goes up. There will be some tunneling on the either sides. If we come to the this is the ground state wave function, and if we consider the first excited states, it had such type of behavior, and for the finite well the behavior will be like this. And the other higher states, there will be some probability of finding the particle outside the finite potential well. This ends our discussion on the bound state aspects of a rectangular finite potential well, and we have assumed the parity conserving states. If such question comes in exam, then you first argue that since the potential is symmetric, the solution will have a definite parity. So for even parity states, the wave function is phi 1 is equal to a e to the power plus rho x, phi 2 is equal to c cos kx, and phi 3 is equal to simply a e to the power minus rho x, as parity commutes with Hamiltonian in this case. And for all parity state, we will have a is equal to e to the power plus rho x, phi 2 is equal to b sine kx, and phi 3 is equal to minus a e to the power minus rho x, and then follow the calculation that we have done.